Hello everyone, I'm He from Caltech. Today I'm going to present our work on learning a probabilistic strategy for computational imaging sensor selection. In computational imaging, we first collect measurements of a target using a sensing system. And then we use reconstruction algorithms to recover the hidden picture from data. Although it is important to design an intelligent reconstruction algorithm, the design of the sensing system is just as important. This is especially true when we are severely restricted in the number of measurements we can make. For instance, in the fast MRI problem shown here, the scanning pattern of its acquisition space, or so-called K-space, can significantly influence the reconstruction quality. That's also the case for Fourier cytography microscopy, where we need to design the illumination pattern of the LED array for better biotissue imaging. And also for astronomical imaging, for example, very long baseline interferometry, or so-called VLBI. By linking the radio telescopes distributed globally, astronomers have used the VLBI technique to take the first image of a black hole. However, as you can see, VLBI measurements are severely limited. There are many missing data in the Fourier domain measurement. The location of telescopes in the array, which controls the measurement, significantly influences the image reconstruction accuracy. So in future VLBI observations, we would like to add new telescopes to improve the imaging capability. These sites need to be carefully selected since including a new telescope will cost millions to tens of millions of dollars. In many linear reconstruction problems, the optimal sensor selection could be analytically solved based on the compressed sensing theory. However, for computational imaging problems with a nonlinear fold model or complicated noise, such as in the case of VLBI imaging, this is not trivial. The telescope selection highly depends on the reconstruction algorithm. So here, we propose to tackle the computational imaging sensor selection by a joint optimization of the sensing system and the reconstruction method. Rearranging the blocks in the computational imaging system, it is not hard to see that the architecture is very similar to an autoencoder. The sensing system is the encoder, which finds the best representation of the measurements, and the reconstruction algorithm is the decoder, which recovers images from limited measurement. Therefore, we can formulate the sensor design problem as a deep learning problem and co-design the sensing system and the reconstruction method. Analogous to classical autoencoder, both encoder and the decoder can be represented by deep neural networks. However, unlike in a standard deep learning autoencoder, since we aim to eventually build the design learned by our encoder, its architecture must lead to designs that are physically plausible. Let's zoom in. This is the architecture of our proposed physics-constrained encoder. We first include a physics-based forward model that simulates all the possible measurements of an image. These measurements could be highly nonlinear, noisy, and correlated. In addition, we also include a trainable block that samples the sensors, and therefore selects samples from the measurements, because sometimes many sensor network designs are equally good. Here, we propose to represent the sensor selection strategy as a probability distribution to explore multiple designs simultaneously. Every time we draw a sample from the distribution, we get a new design of the sensor network, and we hope that each design performs well for the reconstruction. This probabilistic sensor selection strategy is modeled as a binary, fully connected IC model. In the IC model, each sensor has an activity parameter, representing how important it is to include this sensor in the network. Each pair of sensors has a corresponding correlation parameter, representing the probability that two sensors are selected or excluded simultaneously. During autoencoder's training, the IC model distribution can be sampled using a Markov chain Monte Carlo method. In MCMC, the sample is iteratively updated from a conditional distribution based on the last step. You can also interpret the sample update as a function of the last step sample and the random perturbation U. Therefore, we can enroll the MCMC sampler as an MCMC sampling network where each layer represents a MCMC sampling iteration. It takes the sample from the last step and the random perturbation as the inputs, and outputs an updated sensor selection design. All layers have shared trainable weights, which adjust the activity and correlation parameters in an Ising model. We've now defined the physics-constrained encoder. As for the decoder, the reconstruction method, we can use any suitable deep learning framework according to specific applications. The training loss of this autoencoder consists of 3 terms. In addition to maximizing the similarity between the true image and the reconstructed image, we also introduced 2 additional loss terms to regularize the sensor network properties. First is the sensor sparsity, because we want to achieve accurate reconstruction with as few sensors as possible. The second is the sampling diversity. It is especially important because without it, the probabilistic strategy will collapse to a deterministic design. This general framework should be applicable to many computational imaging sensor selection problems. For different applications, we simply need to replace the physics-based forward model in the encoder and the decoder. I will now show you a few examples of what we learned when we used this approach to design the telescope array for VLBI. Before we dive deep into the sensor selection results, let me first briefly introduce the physics meaning of the VLBI measurements. In VLBI, data from 2 telescopes produces a measurement. It is a frequency component of an image in the 2D Fourier domain. The 2D Fourier domain measurement is related to the length and the orientation of the baseline. Longer baseline corresponds to information at higher spatial frequency. With this knowledge, we can now better interpret our results. This is a set of learned Ising model parameters, considering the 12 telescopes marked with red stars on the map. The top figure shows each telescope's activity, and the bottom figure shows the telescope's correlations. In the correlation map, red pixels represent positive correlations, and blue represents negative correlations. Our model successfully learns the strong negative correlation between the collocated sites, SMA and GSMT both in Hawaii, and ALMA and APEX both in Chile. Since collocated sites gave approximately same measurements in the case of simple noise, this makes a lot of sense. We also test the sensor design and many other different scenarios. For instance, in this test, we changed the target reconstruction resolution that we want to achieve. We noticed that the activity of sites like the South Pole Telescope, SPT, decreased substantially when our reconstruction resolution demands are not that challenging. This is reasonable because the South Pole Telescope provides most of our long baselines. That corresponds to high spatial frequency measurements. These 2 tests allow us to demonstrate our method in scenarios that we understand what we expect to recover. But what is more interesting is using this method to recover sensor designs in cases where we don't know what to expect. For example, when we include atmospheric turbulence in the measurements, the phases of the frequency domain measurements are fully contaminated. In this case, the telescope's activities and correlations significantly change. This is something never quantitatively studied before. We found that telescopes that were previously negatively correlated, such as LMT and OVO, become positively correlated, and more important with atmospheric noise. This suggests short baselines may be very important for calibrating atmospheric phase errors. We also investigate potential site locations for expanding the EHT array in the future. We mark sites that do not currently have an operating telescope in yellow. Of these potential sites, our model finds that adding a telescope in South Africa would give the biggest boost to the reconstruction quality. However, more factors should be considered in the proposed model before we draw a final conclusion about which telescope is more important, such as realistic atmospheric noise, weather assumptions, the science target's evolution, and both social and economic cost. We also explore the possibility for replacing the reconstruction method with a feature extractor and a classifier. For example, the black holes could be classified into 2 classes, mad and sane. we train our autoencoder to accomplish this classification task instead of imaging task. And here are the design results. For this particular classification task, the activity and correlation parameters are similar. However, in the classification task, the participation of telescopes appears more equally distributed, whereas in the imaging task, certain telescopes were more important. Although we merely discussed the sensor selection policy until now, the reconstruction neural network is also quite useful. In fact, we recently used this learned network to help plan observations for the Event Horizon telescope. Performing an observation run is quite costly since we are cooperating the telescopes across the globe. So, the Event Horizon telescope would like to optimize which day it observes based on the weather predictions. Every day, we receive a weather report that tells us which telescopes will likely to drop out due to bad weather. For example, on April 4th of this year, we saw that the LMT telescope in Mexico had bad weather. Since our reconstruction network is jointly trained with a probability distribution, it can roughly evaluate the imaging quality for array configuration without LMT and quickly give a prediction of the imaging score. These are the reconstruction predictions for 10 simulation images. Without LMT, the reconstruction quality is pretty bad, so we decided not to trigger on this day. It was exciting to see that our method being used for the real 2020 Event Horizon Telescope rehearsal observations. In our future work, we hope to apply this method to more computational imaging sensor selection applications, such as fast MRI and Fourier photogrametry. Feel free to check our website for further information and code. Thank you. I'd like to take any questions.